In this video, we saw for the dynamics for the motivating case study using eigenvector-eigenvalue analysis. We briefly review the model. You are managing an internet data storage company that provides users access to their data online. It's as though they virtually plug into their memory sticks by logging onto your website. You have XP customers paying for premium accounts, and you have XF freeloaders using an introductory account with a limited data storage capacity. You need to know how the composition of your user base will change with time so that your accounting staff can determine whether the revenues from the paying customers will be able to sustain the expenses incurred by providing both premium and free services. To predict how your customer base will change in time, we need to enumerate processes that can contribute to the dynamics of your customer population. A paying customer can recruit a friend to try out your service. For simplicity, say that in any given month, a fraction rho of the paying customer population persuades a new customer to sign up for free service. For example, if the fraction rho is 3/8, then 3 out of 8 of the paying customers initially present at the beginning of the month succeed in each persuading one friend to join the free customer base by the beginning of the following month. The hope is that customers who try the free service will like it enough to sign up for premium access. Let's say that a fraction upsilon of the free customer base upgrades each month. For example, if upsilon is 2/9, then 2 out of 9 non-paying customers present at the beginning of a given month will get excited about your service and join the paying customer base by the beginning of the following month. Unfortunately, some paying customers might decide they no longer need premium service. Let's say that a fraction delta of the paying customer base downgrades from paid to free accounts. If, for example, delta is 1/4, then 2 out of 8 customers paying at the beginning of a given month will have left the paid subscriber roles by the beginning of the following month. Even non-paying users might choose to cancel their accounts. Let's say that a fraction alpha of the non-paying customer base cancels its accounts each month. If, for example, alpha is 2/9, then 2 out of 9 customers who were signed up for free accounts at the beginning of a month will have completely closed their accounts by the beginning of the following month. The table of events or reactions can be written as dynamics in discrete steps in time. The non-paying and paying populations XF and XP at time t plus delta t can differ from the values of XF and XP at time t, owing in part to recruitment, owing in part to upgrades, owing in part to downgrades, and owing in part to attrition, meaning the cancellation of free accounts. The time step delta t is a month because we are tracking changes in the subscriber base from month to month. We want to express the dynamics of these populations of customers in a simple way. Recognize that the expression of the populations XF and XP at time t plus delta t as linear combinations of the populations XF and XP at time t can be formatted more legibly in matrix notation. The condition of the subscriber base at a given time t can be thought of as a vector x with components xf of t and xp of t, meaning that vector x of t is a linear combination of some abstract basis vectors capital F and capital P. The matrix with elements 1 minus upsilon minus alpha, rho plus delta, upsilon, and 1 minus delta describes a step in time of 1 month. Repeated applications of the matrix represent repeated advances of time in steps of 1 month. For example, multiplying the initial vector components xf and xp evaluated at time t by m copies of the matrix produces the subscriber base at time t plus m additional months. Before we do a lot of algebra to analyze repeated matrix multiplication, let's think about the dynamics of the system qualitatively. Let's say we send out early invitations to get users to try our service for free, so we have capital N non-paying users at the beginning of the month we officially launch. We can visualize the state of the subscriber base by plotting the paying customer population against the non-paying or free user population, with both XF and XP normalized by dividing by capital N, the inaugural number of non-paying users. We are using the components xf and xp, to be more accurate normalized versions of these components, to establish a coordinate grid for specifying the state of the subscriber base at different times. Initially, the state of the system corresponds to this pink arrow. No customers have yet signed up for paid service. We only have the non-paying customers who responded to our pre-launch invitations. Some non-paying customers will enjoy the free service enough to sign up for premium service. Transfer of subscribers from the non-paying to the paying population corresponds to diagonal motion northwest. Some non-paying customers, unfortunately, will lose interest and cancel their accounts. Loss of non-paying customers corresponds to horizontal motion purely to the west. The state of the system thus moves northwest, a little more west than north, going into the next month. Now that a paying customer base has been at least temporarily established, satisfied paying customers can start to recruit their friends to try the free service. Increasing the number of non-paying users corresponds to horizontal easterly motion on this grid. This eastward motion can start to compensate for some of the westerly motion corresponding to the loss of non-paying customers who cancel their free accounts. As the non-paying customer base swells, it then increasingly feeds into the paying customer base. As we said, movement from the non-paying to the paying customer base corresponds to northwesterly motion. Again, as the paying population expands, it helps to recruit more free users corresponding to eastward motion. Together, this northwesterly and easterly motion can produce a net movement, for example, that eventually points in a northeasterly direction. This movement can point noticeably toward the east if paying customers recruit new non-paying customers efficiently. A subscriber base composed purely of non-paying customers generates paying customers because some of the non-paying customers upgrade their accounts. A subscriber base composed purely of paying customers would generate non-paying customers in part because satisfied paying customers recruit friends to sign up for free service, and in part because less satisfied paying customers downgrade to unpaid accounts. Neither pure population remains pure. At some intermediate composition consisting of both non-paying subscribers and paying subscribers, the time rate of contribution to the non-paying population from the paying population in a sense balances the contribution to the paying population from the non-paying population, so that the subscriber base composition remains unchanged. This statement is a little crude because we neglected to mention the attrition of non-paying customers, but we've captured the basic intuition. Pure populations tend to generate their initially missing counterparts. With time, the state of the overall subscriber base eventually becomes arbitrarily close to a constant proportion of non-paying and paying subscribers. This is why the purple arrows representing the state of the system at very late times point at basically the same angle. They indicate a basically constant proportion of xf versus xp. At late times, we need not track changes in population composition. We do not need to track changes in the directions of the purple arrows. The problem is reduced to merely solving for the scaling of the lengths of the purple arrows, meaning calculating the common, same fraction by which both the non-paying population xf and the paying population xp increase each month. Let's use green vector v to denote vectors that have this special property of those vectors corresponding to late times, namely the property that these vectors are merely lengthened by a scale factor lambda, not rotated when acted upon by operator A, where A hat is the operator relating the state of the subscriber base in one month to its state in the following month. What is the population composition embodied by V, and what is the corresponding scale factor lambda by which the population increases month after month? Insert the identity operator I hat in front of vector V. The identity operator is defined as the operator that, given a vector V, spits out the same vector V. It neither rotates nor scales the vector it is given. Writing out I hat is like multiplying by 1. Subtract the vector lambda I hat v from both sides, leaving on the right-hand side a vector with components equal to 0. Factor out the vector v. You may wish to use matrix representation to check that it is sensible to talk about factoring out a vector that is multiplied individually by a hat and by b hat. We can represent a hat, I hat, and vector v using matrices and column vectors. Check that the identity matrix is, in fact, the matrix that does nothing to a column vector. For legibility, remove the subscripts in the matrix for A by renaming A11 and so forth with A, B, C, and D. Element by element subtraction gives this thing. Note that the minus lambdas are attached only to the northwestern and southeastern elements. The line formed by these elements is called the main diagonal. The matrix equation corresponds to this system of two equations written with explicit plus signs. What is the population composition embodied by V, and what is the corresponding scale factor lambda by which the population increases month after month? Working through this slide, we will solve these equations implicitly assuming that some numbers are non-zero. You should probably check whether these assumptions are valid when using similar calculations for specific applications. Multiply the top equation by D minus lambda. Multiply the bottom equation by B. Subtract the bottom equation from the top. Notice that the stuff attached to the component VP in the two equations cancels. This equation says that the product of the stuff in the square bracket and the component VF is 0. One possibility is that the stuff in the square bracket is 0. Another possibility is that the component VF is 0. Yet another possibility is that the stuff in the bracket and the component are each 0. We intuited that the long-term population composition would include both paying and non-paying customers, so the non-paying population should be greater than 0. So require that the stuff in the square brackets is 0. Foil the factors in the parentheses and then organize the quadratic equation in descending powers of lambda. The quadratic formula has two roots indicating possibly two population scaling factors of interest. Here we've just FOILed and distributively multiplied some stuff in the square root. Cancel out a couple copies of AD. The remaining stuff containing A and D can be reverse FOILed into two factors of A minus D. We can now substitute the color-coded Greek letter parameters from the matrix in the footnote at the bottom of the slide. There are two possibly relevant scale factors lambda. To see what lambda plus and lambda minus tell us about green vectors, substitute the lambdas back into the matrix equation representing the vector equation at the top of the slide. The highlighted numbers in the northern row of the square matrix, the entirety of the green column vector, and the northern 0 in the 0 column vector correspond to this equation. Move the term with VF to the right-hand side and isolate VP by dividing both sides by B. We will use the cooking show trick of having a version of the pot that has already been stewing for 2 hours to skip to the result of combining this equation with the definitions for the lambdas and the Greek letter version of A. VP, the paying customer population, is some gobbledygook of constant coefficients multiplied by VF, the non-paying customer population. If we are talking about lambda plus, the corresponding V plus P and V plus F are related by choosing the plus in the plus-minus sign in front of the square root. If we are talking instead about lambda minus, the corresponding V minus P and V minus F are related by choosing the minus in the plus-minus sign in front of the square root. This equation prescribes a ratio between the paying and non-paying components of the vector V. Even if we momentarily confine attention to the plus case, many different vectors, distinguished according to length, can satisfy this equation. This is because vectors that have different lengths can nonetheless share the same ratio between non-paying and paying components. In the following, we will speak with language and tone as though the only distinction we cared about were the direction in which a vector pointed. It will sound as though we thought that two vectors were different only by virtue of differing orientations, as though we were unfamiliar with distinguishing vectors based on length scaling. This confusing form of communication is culturally common in this kind of analysis. Let's rename the gobbledygook Q plus or minus. There are two special scale factors. Each lambda corresponds to its own special vector v. Unless something is hokey, the two vectors v point in different directions and can serve as a basis for establishing a coordinate grid for describing the state of the subscriber base. Here are two green vectors with directional orientations that are meant to display the ratios between vp and vf prescribed by q plus or minus. They can form a coordinate grid where, for example, the initial pink vector representing the inaugural subscriber base is a linear combination of both lime and olive pieces. We will now use the special lime and green vectors to describe the dynamics of the system, not only at the late times that inspired their discovery, but for general time. The state of the population is abstracted as a vector x. The weighting coefficient on some abstract vector called f is xf, the non-paying population, and the weighting coefficient on some abstract vector called p is x sub p, the paying population. We've been considering just for example the initial condition where our marketing before company launch has gathered an inaugural base of subscribers using free trial accounts. The initial condition at launch places all of these n inaugural subscribers in the coefficient for the vector f and none of them on the vector p. This is some linear combination of the lime and olive basis vectors, where the letter c is an uncreative abbreviation for the word coefficient. As a simplifying convention, we write the coefficients for this linear combination using explicit factors of n, so we can do some cancellation. The lime and olive vectors can themselves be expressed as linear combinations of the vectors f and p. In other words, vectors from one basis set can be described as linear combinations of vectors from another basis set. The idea of a lime vector and an olive vector is a bit ambiguous. At the top of the slide, we prescribe two ratios between the paying and non-paying components of the subscriber base, one ratio for the lime or plus vector and another ratio for the olive or minus vector. These ratios are specified by q plus and q minus. However, each of these ratios is satisfied by lots of vectors differing in length. We choose to say we are looking at the situation for which the non-paying components of the lime and olive vectors, meaning both v plus f and v minus f, are 1. The paying components are then necessarily q plus or q minus. Collect terms inside a set of parentheses in front of vector f and a set of parentheses in front of vector p. Compare the left and right-hand sides of the equation and recognize from looking at stuff attached to vector f that c plus plus c minus equals 1, and recognize from looking at stuff attached to p that c plus q plus plus c minus q minus equals 0. We are keeping an expression at the top of the screen to remind ourselves that we are expressing the state vector at initial time t as a linear combination of lime and olive vectors. Rearrange the equation on the right so as to express c plus in terms of c minus. Eliminate c plus in the equation on the left by substituting in the expression for c plus on the right. Factor out the c minus. Cosmetically rearrange so that it will look prettier when we divide the stuff in parentheses to solve for c minus. The solution for c minus can then be used to solve for c plus by substituting into the equation on the right. Using the expressions for c plus and c minus we have just derived, we can express the initial state of the population fully in terms of the initial population size n, the lime and olive vectors, and the Greek letter parameters in the equation in the footnote. Here the Greek letters are hidden in the q's to save space. A month after initial time t, the vector x has moved to a hat x, which is like hitting individually the lime and olive vectors with a hat. We are working with a linear operator that can act on pieces of a sum individually and pass through multiplying coefficients. A hat tickles out from the lime vector a multiplicative scaling of lambda plus, and tickles out from the olive vector a multiplicative scaling of lambda minus. This is nothing more than the equation relating a hat, the green vector v, and the lambdas at the top of the page. The state of the subscriber base after another month has elapsed can be calculated by hitting again with another a hat on both sides of the equation. Again, this spits out a lambda plus in front of the lime vector and spits out a lambda minus in front of the olive vector. And the state of the subscriber base after yet another month can be calculated by hitting both sides of the equation with another a hat in the same way, which spits out another pair of lambdas. Continuing the pattern, the population of customers at capital M months after initial time t is a linear combination of lime and green vectors, with lambda plus and lambda minus taken to the mth power, situated as shown inside the linear combination coefficients. It will turn out, for the numerical values we will explore later, that lambda plus is greater than lambda minus. As capital M becomes arbitrarily large, the m powers of lambda plus become arbitrarily many times larger than the m powers of lambda minus. At long times, the state vector x is approximated by a stretching out version of the lime vector. Unless the initial condition at time t is constructed with precisely no amount of the lime vector, meaning the one of the two green basis vectors with greatest lambda value, will dominate. Substituting for the lime and olive vectors their specifications as linear combinations of the vectors f and p, and then recognizing the pieces sitting in front of capital F's as the component xf, while also recognizing the pieces sitting in front of the capital P's as the component xp, we obtain kind of simple equations for the non-paying and paying subscriber populations at any number of months capital M following the initial time t. It was somewhat time-consuming to calculate the capital Q's in terms of the Greek letter parameters in the footnote, but as our reward, we have obtained expressions for the subscriber base at any number of months capital M, and these expressions are reasonably compact and easy to work with on a handheld calculator. These expressions are more pleasant to work with at large numbers of capital M than manually multiplying the matrices together in the footnote. Unless, of course, you really like pointing with pairs of fingers at elements inside square matrices and making matrix multiplication gestures. To study these dynamics visually, we write out expressions for the lambdas and q's in terms of the Greek letter parameters and choose some trial values for the parameters for recruitment, upgrades, downgrades, and service cancellation. We use the same coordinate grid from our earlier intuitive discussion, tracking the normalized paying and non-paying subscriber populations. Our inaugural user base lies fully in the F direction. Transient behavior moves northwest and then connects to long-term behavior characterized by what has turned out to be one of the green vectors we have analyzed. Almost as though contrived, this numerical plot is miraculously identical to our anticipatory intuitions. The green vectors are called eigenvectors. In this example, they are specified concretely in terms of the Greek letters with the help of the capital Q's. The scaling factors associated with these eigenvectors are called eigenvalues. When we refer to eigenvalue-eigenvector analysis in the future, we will mean calculating the eigenvalues and determining their associated eigenvectors. Using eigenvectors and eigenvalues, we can express the dynamics modeled using a linear operator in a convenient and relatively simple way. In other words, the eigenvectors are in some sense special for the operator. The eigenvectors of an operator are those special vectors, if they exist, that when acted upon by a linear operator of interest spit back out vectors with the same direction but possibly altered length. The length scaling factor associated with the action of the operator for a particular eigenvector is the eigenvalue associated with that eigenvector. It may relieve or perhaps exacerbate confusion to remind ourselves at this point that it is culturally accepted to speak of an eigenvector when in fact one is thinking of an entire family of arrows, all pointing in the same direction or perhaps exactly reversed, but differing in length. Plural singulars are entertaining, especially when working with mathematical concepts that would already be exciting to digest even if communication were precise. In a system with more than one moving part, the dynamics of each part might depend on the states of all of the parts taken together. The case study that motivated this deck of slides is an example of a class of systems where events occur resulting from the activities of fixed proportions of component populations. When working with such systems, the habitats, animals, and circus tricks of linear algebra provide a powerful way to solve for the dynamics of the individual parts and thus of the integrated system.